Today, I'd like to talk about the idea of continuity for functions of more than one independent variable. As usual, I'll stick to two variables, although all of the ideas extend to any finite number. If you haven't watched the video on limits of such functions, be sure to give that a look. In analogy with what we did in Calc 1, we'll say that f of x and y is continuous at AB. In analogy with what we did in the first semester, I'm going to say that a function f is continuous at AB if three things are true. Firstly, the function value at AB has to make sense. Secondly, the limit as xy approaches AB of the function values must exist, and the limit has to equal the function value. Before we go on, I want to make a comment about that middle condition. In view of the definition of the limit, I have to look at all points that are close to the point AB but not equal to AB. I have to be able to look at all of their function values and see if, as you approach the point AB, if all of those function values begin to resemble a certain number, which we call the limit. That means there has to be a disk centered at AB inside of which the function value is defined at every point. There can't be any bad spots arbitrarily close to point AB. Now, that's not to say that there can't be some bad spots of the function. I just have to be able to construct a little particular disk in which the function makes sense, except maybe right at AB. As a typical example of this sort of thing, let's discuss the continuity of the function f of x and y equals x divided by x minus y. Since this is a rational function, a ratio of two polynomials, the only possible places where it can be non-continuous would be places where the denominator is equal to 0. So I can say definitely that f is continuous at all xy, except places where the x and the y coordinates are the same. What about x equals y? Does the limit exist, possibly? For example, I might look at the point x equal 3, y equal 3, and think of the limit of f of x and y as x approaches 3 and y approaches 3. Strictly speaking, we would have to say that the limit doesn't exist, because no matter how small a disk you draw centered at 3, 3, there will be points nearby where the x coordinate and the y coordinate are the same, and the function is not defined for all xy's inside the disk. This limit doesn't exist. An interesting example is f of x and y equals x squared minus y squared over x minus y. Obviously, this function is not going to be continuous if x is equal to y along that same straight line again, but if you are not located at such a spot, then something interesting happens. If x is not equal to y, then we can do the usual algebra manipulation and find out that f of x and y will just be x plus y. It's worth remembering that the graph of z equals x plus y is a plane, so strictly speaking, the graph of this function should look just like the graph of z equals x plus y, except a single straight line has been removed. Let's have a look at that. in this one, obviously, f of x and y is continuous every place except perhaps the origin. The function value doesn't exist, so actually that means the function is not continuous at the origin. But what of the limit? If I get close to the origin, 1 over radical x squared plus y squared becomes indefinitely big. However, as you insert numbers into the cosine function, which can be as large as you care to make them, you will go through multiples of 2 pi. I expect that my graph will have points that are at or nearly at z equals 1, where the cosine is maximum, also where z is negative 1, and I believe that this is going to be the case no matter how close to the origin we get. In the graph that follows, I've adjusted the x and y range to be from negative 1 to 1. This has just been a short video containing some comments on the idea of continuity, which is a natural extension of the idea of limits. Coming up next, partial derivatives. I hope everyone has a good day, and I'll talk to you again soon.